Okay, the length of the spaceship to 3 significant figures. Factor the run slow. All we have to do in this case is just apply the equations that we have there. Beta equals 1 minus the length minus the original length squared. Just gives you, it's 1/2 the length, so this is just 1/2 squared here. That gives you a value, taking the square root of that, 0.866. And then the Lorentz factor, when you, with this as your beta in here, it just gives you a value of 2. Now here we have the Lorentz transformation. The Lorentz transformation equations relate to the space-time coordinates of a single event as seen by observers in 2 different inertial frames, s and s prime, where s prime is moving relative to s with a velocity v in the positive x and x prime direction. 4 coordinates are related by these equations here, and you can see that the spatial values of x and t are intimately involved in both of this equation and this equation. This entanglement right here was a prime message of Einstein's theory, and many people rejected that initially, but has been proven out over time to actually be the case. So the Lorentz transformations in terms of any pair of events with spatial and temporal separations is given by these particular equations right here. Okay? Depending upon which way this is x with the change with respect to x, this is change with respect to x prime, right? So depending upon which way it moves. So observer S reports that an event occurred on an x-axis of his reference frame at x equals 3.00 times 10 to the 8th meters at time t equals 2.50 seconds. Observer S prime and her frame are moving in a positive direction at 0.4 times the speed of light. They start off at the same spot. What are the spatial and temporal coordinates of the event according to S prime? And if instead they were moving in a negative direction, what are they according to her? Okay? So the coincidence of this right here, of the initial conditions, you can apply this without any additional terms. So you apply these directly. It gives you a V equals plus 0.40 C equals 1.19 times 10 to the 8th meters per second. So in part C, we simply change V to minus V and recalculate the prime values. First of all, the position coordinate measured in the S prime frame is x prime gamma x minus VT, that equation, which is essentially this right here. Gamma is 1 over 1 minus beta squared. Putting those numbers in there, it works out to be 2.7 times 10 to the 5th meters. Okay? That is a fairly small value compared to the value for x, right? 3.0 times 10 to the 8th. That's 3 orders of magnitude smaller. 3 orders of magnitude smaller. Where we conclude the numerical result is essentially, depending upon how precise the value of V is used, is not meaningful in the significant figure sense and should be set equal to 0. That is, it is consistent with 0 in the view of the statistical uncertainty involved. Now, the time coordinate measured is not 0. Putting this into the other equation, right, where we now put these other values in there, we get that t prime is 2.29 seconds. Going in the other direction, this now becomes non-trivial, okay, because it's plus that amount. And so it's going to be 6.54 times 10 to the 8th meters. And similarly, for the t, that t is now 3.16. Okay, now a clock moves along the x-axis at a speed of 0.6 times the speed of light. It reads 0 as it passes the origin. Calculate the clock's Lorentz factor, and what time does the clock read as it passes x equals 150 meters. So the Lorentz factor is given by gamma equals 1 over the square root of 1 minus beta squared, which is 1 over the square root of 1 minus 0.6 squared, right? That's 1.25. In the unprimed frame, the time for the clock to travel is 180 meters. So, okay. So t equals x over the speed, right? V. So it's 180 meters, 0.6 times 3.0 times 10 to the 8th meters per second. Okay, that's what V is going to equal, is 1.00 times 10 to the minus 6 seconds. The proper time interval between the two events is measured by the clock itself. The reading on the clock at the beginning of the interval is 0, so the reading at the end is this t value divided by gamma, which is the 1.0 times 10 to the minus 6 seconds divided by this gamma value right here, which is 8.0 times 10 to the minus 7th seconds. Okay? So, when a particle is moving with speed u prime in the positive x direction in an inertial reference frame, s prime, that itself is moving with the speed v parallel to the direction x of the, this is the speed u of the, is measured as follows. Okay, so now we're talking about two different ones, both moving. This is u equals u prime plus v plus divided by 1 plus u times v divided by c squared. Be careful to substitute the correct signs for the velocities. This equation reduces the classical or Galileo type of velocity of this type right here. Okay, so it's the denominator right here that changes the relativity portion from what Galileo would have calculated. Okay, so in other words, relativistic equation is correct for all physically possible speeds, but the classical equation is approximately correct for speeds much less than c, which is all Galileo was interested in anyway, right? So the stellar system Q1 moves away from us at a speed of 0.8 times the speed of light. Stellar system Q2, which lies in the same direction but is closer to us, moves away from us at a speed of 0.4 times the speed of light. What multiple of c gives the speed of Q2 as measured from an observer in the reference frame Q1? So using that equation that we have, okay, it's always going to be in a positive direction. So v is 0.4, u is 0.8, both of them times the speed of light, with three significant figures understood. We saw the velocity Q2 relative to that. So we put it into that equation that we had before. It's 0.8 minus 0.4, okay? 1 minus 0.8 times 0.4. And so it equals 0.588 in a direction away from Earth, okay? That's how, what is observed like from the condition number, from position number 1. Now we have an armada of spaceships. There's so many of them that it's 1.00 light years long as measured from its rest frame. And it moves with the speed of 0.8 times the speed of light relative to the ground station in frame S. A messenger travels from the rear of the armada to the front at the speed of 0.95 times the speed of light relative to S. How long is the trip measured in the rest frame of the messenger, the rest frame of the armada, and an observer in the ground frame S? So the messenger's rest system, we'll call S sub m, is the velocity of the armada, okay, v prime, and the velocity of the armada is v, which is v minus v of the messenger, 1 minus the two of them together, multiplied together, divided by c squared. So it's 0.8 minus 0.95c. and this is 0.8 times 0.95 divided by c squared, and this is subtracted from 1. So that equals minus 0.625 c. So the length of the armada is, again, we have to use the Lorentz factor here, and that is this value right here, okay, times v, okay, and so that gives us 0.781 light years. Now, the length of the trip is t prime, this L prime, how much it has shrunk, divided the absolute value of this right here. So it's 1.25 years for him to go from the front of the armada to from the back of the armada to the front of the armada. In the armada's rest frame called SA, the velocity of the messenger is given by this right here. Calculates out to be 0.625 c. And now the length of the trip is 1.60 years in that reference frame. Okay? And then finally, measuring the system, the length of the armada is it's 1 light year divided by the gamma, right? So the length of the armada in terms of the reference of what he is doing is 0.60 light years. So the length of the trip is t equals this length, the velocity of the messenger minus the velocity of the armada, right? And that gives you 4 years. We've had before the Doppler effect for sound. Now we're going to see what the Doppler effect is for light. So when a light source and a light detector move relative to each other, the wavelength of light as measured in the rest frame of the source is the proper wavelength, lambda 0, right? The detected wavelength is either longer, a red shift, or shorter, a blue shift, depending upon whether the source detector separation is increasing or decreasing. So when the separation is increasing, the wavelengths are related by this right here. It's 1 plus beta, 1 minus beta, and the square root of that times the proper wavelength. So with beta equal to this V over C, all right, relative radio speed for the source and detector. If the separation is decreasing, the signs in front of the beta symbol are reversed. Okay, if the separation is decreasing, they're getting closer. For speeds much less than c, the speed of light, the magnitude of the Doppler wavelength shift is approximately related by this equation right here. Okay, so the transverse Doppler effect. In this figure, a source S is moving past the detector D. When S reaches point P, the velocity S is perpendicular to the line joining P and D. At that instant, S is moving neither toward nor away from D. If the source is emitting sound waves of frequency F0, D detects the frequency with no Doppler effect when it intercepts the waves that were emitted at point P. However, if the source is emitting light waves, there is still a Doppler effect called the transverse Doppler effect. The detected frequency is given by this equation right here, F equals F0 times the square root of 1 minus beta squared. For low speeds, this equation can be expanded in a power series in B and approximated by this right here. This is at low speeds. Here the first term is what we'd expect for sound waves. And again, for relativistic effect for low speed light sources and detectors appears to be beta squared. So, a sodium light source moves in a horizontal circle at a constant speed of 0.1 times the speed of light, while emitting light at a proper wavelength, L0, lambda 0, equals 589 nanometers. Whoops. The wavelength is measured for the light by a detector fixed at the center of the circle. What is the wavelength shift? And we'll answer that in the next video.